students, in this class we are going to discuss the most important and popular biasing technique, self-bias or emitter bias, and which is also called as a voltage divider bias. Already we have discussed fixed bias and collector to base bias, and they are having their own disadvantages. The operating point is actually not stable in those techniques. Operating point changes with the temperature and as well as beta. But whereas in the case of the self-bias or emitter bias, we are having so many advantages. As usual, you try to take this common emitter configuration. In this common emitter configuration, emitter is common for both input and output, and we are taking a emitter resistance also here. This emitter resistance can be acting like a feedback resistor for this entire network, and RC as usual it is a load resistance, and you are taking the output at the collector. That's why it is common emitter configuration. Whatever the base resistance you have seen in the previous techniques, it is divided into two resistors here, R1 as well as R2. And here the assumption is R2 is very greater than this R1, and the base current is very less compared to the currents that are coming here. So if you take this I1 and I2, these are the currents in the resistor R1 and this is R2. The assumption is here I1 is approximately equal to I2, and which is very greater than the base current IB. Because whenever you are taking these two input terminals here, these are the input terminals, let me say this is nothing but the A and B. And if you are seeing this input resistance to this network, it is very high because of this emitter resistor. So if you calculate here, whatever the Rin you are taking here, this is nothing but the Rin. Rin input resistance will be 1 plus beta times Re. Re is nothing but the emitter resistance here. So that's why the current that is drawing from this point is very less compared to your I1 and I2. And one more thing is here, it is a emitter bias. It is called as an emitter bias circuit. The reason is very simple. Whatever the currents that are flowing through this Re, from this place IB is coming here, IC is coming here, total current is IB plus IC. This IB plus IC is actually entering into this Re and producing a voltage drop across this. This is plus and minus. This voltage drop actually reverse biasing this network. So it is actually coming as a source to this input so that the input biasing will be reduced. The emitter junction forward biasing will be reduced because of this voltage drop. That means input current will be reduced. In this way, actually it is controlling this temperature variation. Let me say, if the temperature increases, IC also increases as usual using the concept of thermal runaway. If IC increases means this is IC, automatically IE also increases because IB plus IE is equal to IC is equal to IE. Because of the temperature, if IC increases, IE also increases because IE is equal to IB plus IC. If IE increases, the voltage drop across RE increases, so the feedback voltage increases here. The reverse feedback voltage increases here. That's why forward biasing will be reduced on this junction. So the input current decreases. Therefore, IB decreases. If the input current decreases, automatically IC also decreases. In this way, the temperature variation will be controlled here. So that's the reason it is most popular. The emitter itself is actually controlling this temperature variation, and the resistor R2 actually giving the biasing for this network. So it is called as a self-bias or emitter bias, and the biasing is provided by the two resistors R1 and R2. So voltage is dividing across R1 and R2. Some voltage, let it be V1, let it be V2. So the voltage is actually divided into two things. So that's why it is called as a two voltage divider bias also. So that is the reason we have named the circuit as self-bias, emitter bias and voltage divider bias. So now let us analyze this circuit. because we have to fix the operating point Q. Operating point Q means it is having the coordinates of VCE as well as IC. You have to calculate these two parameters, and after fixing, you have to see either any variation with the temperature or beta also. So with temperature, there is no variation at all because emitter resistance is taking care of it. So now, as usual, just like other biasing techniques, for calculating this VC and IC, let us apply the Kirchhoff's voltage law to the input side as well as to the output side. But remember, my dear friends, can you apply the Kirchhoff's voltage law to this? You cannot. You cannot apply directly to this. So that is the reason what we are doing is, we are going to use the Thevenin's theorem here. So by using this Thevenin's theorem, I would like to convert this circuit into a different format. So what is the Thevenin's theorem? Thevenin's theorem is very simple. If you are taking any Thevenin's theorem, any huge network can be replaced by a voltage source in series with a resistance. In series with a resistance. This is nothing but the Thevenin's side representation. So what is this voltage source here? If you apply the Thevenin's theorem to the input loop here, what is this voltage source? This voltage source is nothing but the voltage across this. What is the voltage across this? Voltage across this is equal to VCC divided by R1 plus R2. This is the current flowing through this. That is nothing but the I2 or I1, whatever it may be. So I2 is equal to VCC by R1 plus R2. This is the current flowing through this into R2. So that is the reason I can say, let it be, this is the voltage V. V is equal to VCC divided by the resistances. VCC by R1 plus R2 multiplied with R2, because this is the voltage across R2 here. Then just by seeing this, you can understand this is the voltage source. Then Thevenin's theorem requires a resistance in series with this. What is that resistance? That resistance is nothing but the base resistance RB. This RB will be equal to the parallel combination of R1 and R2. So you can say RB is equal to R1 in parallel with R2. So the input side totally you can convert into a Thevenin source in series with a resistance. So the source is nothing but this VCC into R2 by R1 plus R2, and the base resistance is R1 in parallel with R2. So as soon as you are seeing the values of R1 and R2, you have to calculate the base resistance by taking the parallel resistance formula, and the voltage means it is a voltage divider network. So this entire circuit can be now redrawn as, you can see this, the circuit will be like this. This is equal to, the circuit is equal to. So you can say that as usual, this is the common emitter amplifier with resistor, this is RE, and the load resistance RC here, this is RC, and output you are taking from this place, that is called VCE, and inside input side you are having, this is RB, and the voltage source representation is nothing but V. This is nothing but the V. So what is this V? V means VCC into R2 by R1 plus R2. And what is this RB? RB means R1 in parallel with R2. And this is the resistance. This is the resistance here. And the VCC as usual you are applying here. And this is IC, collector current. And this is nothing but the base current. And sum of the base current and collector current will come to this emitter, IB plus IC, which is nothing but your IE. So now if you take this circuit, it is very easy to apply your Kirchhoff's voltage law. What is the technique I am telling you? Just write KVL to the input loop and output loop. If you write the KVL to the input loop, you can calculate your base current. From base current, you can calculate IC. So from the output loop, you can calculate VCE also. So now here, if you are taking this KVL to the input loop, KVL for input loop, then you can understand voltage V is equal to IBRB plus IBR plus. What is this voltage? This is the voltage between the base and emitter, VBE. It is always 0.6 for silicon and 0.3 for germanium. So plus VBE plus, you can say this is RE into RE into IB plus IC. So this is the KVL equation for the input loop. So from this what you have to say, VBE can be neglected if you want, it is only 0.3 or 0.6, otherwise you can put here also. So I can say that this is V minus VBE is equal to, I can take IB as a common, IB into RB plus RE plus this is IC into RE. Then what you can say, I want IB base current is equal to V minus VBE divided by I can say this is minus IC RE divided by RB plus RE. This is the base current. Once the base current is known to you, happily you can calculate from the base current, you can calculate IC. So IC is equal to beta times IB. So this is the way of calculating your collector current from the input loop. What is the technique I told you? In the self bias or emitter bias, the input section should be represented by a voltage source in series with a resistance. The voltage source is nothing but a Thevenin source and Thevenin resistance here. As soon as the values are given to you, you calculate the voltage V here and RB. Just you take the circuit, immediately you can get all these parameters. So IB is equal to V minus VBE by minus ICRE by RB plus RE. Now this is the way of calculating your IB. Once the base current is known to you, then you can calculate your IC also. So how to write down this output loop equation? Output loop equation you can write like this. Now writing the KVL for the output loop, VCC is equal to, applied voltage is equal to ICRC plus this is actually VCE, this is collector terminal and this is emitter terminal, this is VCE plus VCE plus RE into IB plus IC into RE. So this is the way of writing this KVL. This is the KVL for this. Now you can say, I want VCE because this is the operating point coordinate. Therefore, VCE is equal to VCC minus ICRC minus IBRE minus ICRE. Therefore, your VCE is equal to VCC minus ICRC minus ICRE. So you can take this common, RC plus RE minus IB into RE. But remember friends, this IB will be in terms of microamperes and IC will be in terms of milliamperes. So you can neglect this also. This is not having that much of effect. Therefore, your VCE is equal to VCC minus IC into RC plus RE. So you have calculated your VCE also. This is the VCE. So you have calculated VCE and you have calculated IC also. So that is nothing but the coordinates. So in this way you have to calculate the coordinates of an operating point for your circuit. So this is the way of actually calculating the operating point Q. That means the coordinates of VC and IC. Now let me check the temperature variations as well as beta variations. Okay. So we fixed the operating point Q for the self bias or voltage divider bias. Now let us check the temperature variations. Temperature variation in the sense, you see this diagram, if temperature increases, ICBO increases. If ICBO increases, ICEO increases, then IC also increases. If IC increases, here, see here, because of the temperature, if the collector current increases, IC means indirectly IE, because IC is approximately equal to IE, because IB is very, very less. Because of the temperature, if IC increases, then IE also increases. If IE increases, the voltage drop across RE increases. This voltage drop will be applied as a voltage source in the reverse direction of this input so that forward biasing of the junction decreases. If the forward bias decreases, input current IB decreases. That's why I have seen here, if IC increases, IE increases. If IE increases, IE increases, means the voltage drop across the emitter resistor. If the voltage drop across emitter increases, IB decreases because the forward biasing will be decreased. If input current decreases, output current automatically decreases. That means the increase in the IC is balanced by the decrease in IC because of the reverse biasing of the input junction. So that is the reason temperature variation is excellent. Because of the temperature, if IC changes, then IC can be controlled by using this bias. And already you know, because of this temperature variation, IC is equal to beta times IB plus beta plus 1 times ICEO. ICEO. So you can say that ICBO. So you can say that IC is a function of temperature. So IC always changes with temperature. If it is changing with temperature, that can be controlled by using the voltage divider bias, by taking a voltage drop across the emitter resistance. So that's the reason, understand it very clearly. The emitter resistor is always biasing this forward input junction in the reverse direction so that the input current decreases, then automatically output current will be in control. So for this circuit, fixing of the operating point Q is excellent, and temperature variation is also taken care of. And what about the beta variations? Beta variation is also not there. Beta variation comes into the picture whenever the transistor gets damaged. If the transistor is replaced with a transistor of another type, that is beta changes, then only there will be a problem. But here, that variation is also may not be there. If you take the equations of anything, there is no question of beta. Beta is absent in all equations. And by chance, if beta variation is there, that can be controlled by using your IC and IE like this. So that's why beta variation is also excellent. And fixing of the operating point is good. Beta variations is already taken care of. Temperature variation is also taken care of. That's why this self bias or emitter bias, voltage divider bias is the most popular biasing technique. So many times they can ask you explain about this self bias or emitter bias. It is self bias because the biasing is provided by the circuit itself. It is called emitter bias because the emitter is actually biasing the input junction here. And voltage divider bias because the biasing is provided by the dividing network R1 and R2 here. But the only assumption here is the input resistance of this network is very, very greater than this R2 and R1, because in the analysis part we can see whenever you are seeing this input resistance, it is always 1 plus beta times Re. As soon as you are putting an emitter resistance here, the resistance is enhanced by the factor 1 plus beta whenever you are looking from input side like this. So in this way, try to understand this self bias or emitter bias. And most of the times, the people are going to ask you why self bias is much more popular. It is much more popular because it is taken care of all the variations. And whatever the disadvantage you are having in the collector to base bias, that is voltage feedback network. But here no output is connected to the input. So straight away the output will be taken here. So that's the reason the gain is also more in this self bias network. That's why it is a much more popular biasing technique out of all the techniques. So in the next class, we are going to see which biasing technique is the best one. Already with the operation of all the circuits, we concluded that self bias or emitter bias is the most popular. But mathematically also, we can conclude which biasing technique is the most popular technique. So for that, what we do is, we are going to calculate the stability factor for every biasing technique. Stability factors means the variation of IC with reverse saturation current and with your VBE and with your beta. So there are 3 stability factors we are going to discuss: S, S dash, S double dash. And we are going to calculate all these stability factors for all these biasing techniques. If the stability factor is more means it is unstable. Suppose if you are taking 3 biasing techniques, one is getting 5 stability factor, other one is getting 10 and other one is getting 1. 1 means it is the most important and it is actually the preferred biasing technique. So, if the stability factor value is more means it is more unstable. So, the concept of stability factor and actually the calculation of the stability factor for all these biasing circuits we are going to see in the next class. Okay, thank you.